When performing a hypothesis test, what we're trying to do is use data to interrogate whether some particular view about the world, some particular hypothesis about the world, whether it's valid, whether it's well supported, or whether it's not well supported. And so what we are going to need to do is use the data that we can collect to compute things, and then using those things that we're computing to use them to assess how likely that hypothesis actually seems. And anytime that we're computing something from data, we're dealing with statistics, right? We are dealing with computing a statistic. A statistic is something that we're calculating from observable data. And so when we're in the context of hypothesis testing, what we're thinking about is a very specific form of statistics. And notably, we're thinking about what we call test statistics. So in order to run a hypothesis test, we need to be able to compute what we call test statistics in order to assess the evidence that is available within the data. So what is a test statistic? Well, in the framework of hypothesis testing, our ultimate goal is to assess whether the data contradict our stated null hypothesis. So we want to see, do the data that we've collected seem to support the null hypothesis? Do they seem likely if the null hypothesis were true? Or are they in contradiction with this null hypothesis? And in order to do so, what we actually do is we compute a statistic that has a known sampling distribution if we assume that the null hypothesis is true. So the sampling distribution of a statistic is the distribution that that statistic actually follows. Anytime that you take a different sample, you're going to get a different value for your statistic. And so the distribution of the possible values that you can get from your statistic, that's referred to as the sampling distribution. And so the statistic, if it has a known sampling distribution, when we assume that the null hypothesis is true, then we call this a test statistic. Okay, and so there's sort of two critical pieces here, right? The first is that it needs to have this known sampling distribution, but specifically, we want it to have a known sampling distribution if the null hypothesis were actually true. So we assume that the null hypothesis is true, and then we say, well, what is the distribution of this statistic in that situation? Okay, so sort of formally, a test statistic is any statistic that has a completely known distribution, assuming that the null hypothesis is true. And the utility of this is that we're going to then be able to use these statistics in order to assess the likelihood of the null hypothesis sort of indirectly. Okay, so any statistic that has a known sampling distribution, if we assume that the null hypothesis is true, is called a test statistic. Now, importantly, when we're talking about there being a known sampling distribution, what we mean is that there should not be any dependence on unknown parameters, right? So it's not enough to say, well, it's a normal distribution. What we need to say is it's a normal distribution and we know the values for the mean and the variance, right? We need to be able to fully specify this specific distribution. And because we're dealing with this under the null hypothesis, we get to make some assumption about the data, right? This only has to hold if the null hypothesis is actually true, but in that case, then we need to know everything about the distribution. Okay. So in this situation of dealing with a test statistic, we introduce what we call the null distribution. And the null distribution is just sort of a shorthand way of saying the sampling distribution if the null hypothesis is true, right? So the null distribution is the sampling distribution of a test statistic, assuming that the null hypothesis actually holds, right? And so we have the null distribution, which is the distribution of the test statistic under the assumption of the null hypothesis. The sampling distribution is more broad. It is just the distribution of the test statistic generally, but when we assume that the null hypothesis holds, well, then that's going to give us the null distribution. Ultimately, we're going to use the null distribution in order to quantify probabilities in hypothesis testing. So we're going to take our test statistic, we're going to take the null distribution of that test statistic, and then we're going to be able to make statements about the probability of observations based on that null distribution. Okay. Now, sometimes we're going to rely on approximate null distributions in the same way that we might rely on an approximate sampling distribution. So, for instance, you might be able to make use of the central limit theorem to say that the distribution, the sampling distribution of the sample mean is approximately normal. We're going to be able to do similar things with our null distributions. Okay. Now, the good news about test statistics is that if you're testing common parameters, so you're testing the mean, or you're testing a proportion, or you're testing the variance, there are going to be well-established test statistics that the null distribution is already known for. However, the concept of a test statistic is going to expand or extend well beyond the simple parameters that we might be thinking most often about. So we're going to take a look at an example for identifying a test statistic here. And we're in the situation where we have it draws from a normal distribution here, right? So we're assuming that x1 through xn are all drawn from this normal distribution. And importantly, we're saying that the mean is unknown. So we don't know the actual specific value of mu here, right? But we do know the variance, right? So sigma squared, this is just some value that we actually do know the specific value of. And what we want to do is we want to test the null hypothesis mu is equal to 4 versus the alternative that it's not equal to 4. And what we're asked about in this situation is to find a test statistic and the corresponding null distribution for testing this hypothesis, right? So that's what we're actually looking for here. And so in this case, our test statistic should be something that is somehow connected to the parameter that we're actually thinking about, right? Because we ultimately are going to want a statistic that if we assume that mu equals 4, that we then know the distribution of, okay? And because we're thinking about the mean of a population, something that would be really natural for us to think about is, well, what if we were to take, say, x bar, right? And because we're dealing with a normal distribution here, what we know is that x bar has a known sampling distribution, right? So the sampling distribution of x bar is going to be normal with a mean of mu and a variance of sigma squared divided by n. So this is our sampling distribution. Okay, and so we are almost there actually, right? Because this is a statistic with a known sampling distribution, but we're not quite there. Because what we need to be able to do is specify, well, if the null hypothesis is true, what is the distribution of this specific statistic here? And remember that the null hypothesis here, h0, is that mu is equal to 4. And so if we have mu is equal to 4, right? So if we assume that this is true, then we can think about, well, what is this distribution right here? And in particular, we're going to be able to say, well, that's going to be a normal. And here we know that mu is 4, right? So that'll be normal 4. And sigma squared is just some known value, right? So sigma squared over n, that's just a number. Maybe sigma squared is 1, maybe it's 2, whatever it happens to be. This is now a fully specified distribution here. Right? And so what we can say is, well, x bar is a test statistic, okay? Because it's a statistic that we know the distribution of, assuming the null hypothesis is actually true. Okay, so that's sort of the thought process we're going through here. Now we can sort of pull open the response here and sort of walk through it again. The motivation is that because we're interested in the population mean, it's natural for us to consider our sample mean. And we know, because of the normally distributed population, that the sample mean has a normal distribution. If we assume the null hypothesis is true, then we know that mu is equal to 4. And so as a result, we get that x bar follows a null distribution of mean of 4, variance of sigma squared over n. Now it's worth highlighting this notation that we have right here, right? So the tilde symbol, right, actually means distributed as, right? So if we write that x bar tilde normal, right? This means that x bar follows a normal distribution with a mean of mu and a variance of sigma squared over n. If we write the little h0 above the tilde sign, then this specifies that this is the null distribution here. Okay, so this is our null distribution, where you're reading that as under the null hypothesis, x bar has some particular distribution, right? And so that's sort of what we're thinking about with that notation right there. But what we're saying is that the null distribution of this statistic is the normal with a mean of 4 and a variance of sigma squared divided by n, right? So the notation there indicates the null distribution. So this is a perfectly acceptable response to this problem. However, it's actually going to be more common for us to take a slightly different response here. So I'm introducing this test statistic that I'm calling T. And what we do is we take our sample mean, right? So we're starting with x bar, but we're going to subtract off the value under the null hypothesis. So in this case, mu naught is going to be equal to 4 here, right? And then we'll divide by sigma over the square root of n. And the reason that we like to do this statistic instead is because the null distribution ends up being a standard normal, right? A normal 0, 1. And this is going to be slightly more convenient because then we don't need to worry about the mean and the variance being specific values, right? But this is still a statistic here because we can actually calculate this exactly, right? We're taking the x bar, which we can calculate, subtract off 4. That's just a constant. We know the value of sigma. We know the value of n. And so this is going to work equally well, and it comes from the previous result that we actually have right there. Okay. So test statistics are any statistics that we're going to be using in hypothesis testing that have a known sampling distribution when the null hypothesis is true. We call that sampling distribution the null distribution because it's the distribution under the null hypothesis. And by knowing the distribution when the null hypothesis is true, we're able to make probability statements about the statistic, and we're going to be able to assess using those probability statements how likely is it that the null hypothesis were true, or more often, how likely is it that the null hypothesis is not actually true.